In this example, we have two tugboats towing a tanker. So these are the two tugboats and this is the tanker. The tanker has a mass of 20,000 tons. The direction and magnitude of the forces exerted by the tugs are shown in the diagram. So we have 70 kilonewtons from the one at the top, going in the direction of the arrow, and 60 kilonewtons, again going in the direction of the arrow from the bottom. Find the magnitude and direction of the acceleration of the tanker. So we want to find what is the overall effect of the two forces from the two tugboats. In other words, what is the resultant of those two forces? And from that, we can then work out the direction and the magnitude of the acceleration of the tanker. Now, first of all, notice they both act at 30 degrees to a dotted line. However, one of them is pulling harder than the other. So the acceleration of the tanker is not going to be along the dotted line. If they were pulling with the same force and still had the same angle, then yes, then it would be along the dotted line. So the one at the top is pulling slightly harder, so I'm expecting the acceleration to be above the horizontal. Since we're given the mass of the tanker in tons, it's important that we remember 1,000 kilograms is 1 ton. So the mass of the tanker is 20,000 kilograms. In other words, 20 million kilograms. Now the mass of the tanker won't become relevant until the end of the question, when we know the resultant force provided by the two tugs. So let's now focus on figuring out the resultant force. I've introduced a vertical y-axis and horizontal x-axis into the diagram just for the reason that it makes it easier for me to describe what I'm doing. So when I write down what I'm doing, the examiner will understand what it is that I'm trying to do. So let's work out the horizontal component of the resultant force. To do that, we're going to get the horizontal component of both forces. When I say horizontal, I mean when you're looking down on the diagram, looking down on the boats. In other words, in the x direction on the diagram. So that'll be 70,000 cos 30 plus 60,000 again cos 30. The angle is adjacent to the direction in both cases, so cos in both cases. We can simplify this. 70,000 cos 30 plus 60,000 cos 30 is 130,000 cos 30. And we could go one step further. Cos 30 is root 3 over 2. So this is 65,000 multiplied by root 3. So that is the strength of the resultant force in the x direction. Let's now find the strength of the resultant force in the y direction. We're going to have 70,000 sine 30. Or if you wrote cos 60 instead of sine 30, that's absolutely fine. And then it'll be take away 60,000 again sine 30 or cos 60. If you can't remember how to get the sine 30 or the cos 30, then go back to example 1.2.1, the video for that, to remind yourself how to do it. So this is 10,000 sine 30, and since sine 30 is a half, then this is 5,000. Because that's come out positive, that confirms my suspicion that the resultant will act above the x-axis. It has a vertical component which is pointing up, not down. So what I'm going to do now is write down the resultant force, which this time I'm going to call F. I could use any letter I like that hasn't already been used in the question, but I'm going to write it in vector form. You don't have to do it this way, but I think it's a good way of doing it. So I and j are the unit vectors in the x and y directions respectively. So I can write this as 65,000 root 3 times I. Make sure you underline I because it's a vector. Plus 5,000 J. Vectors are really useful when you get used to them. So that is the resultant force. And we've written it in vector notation. That's the resultant of the two forces in the diagram. Now we want to find the magnitude and direction, not of the resultant force, but of the acceleration of the tanker. So think what we've got. We've got the force, well, we've got the resultant force. We're trying to find the acceleration. So if we just had the mass, then we can use Newton's second law, F equals ma, and that will give us everything that we need. And of course we do have the mass of the tanker. So the acceleration, which is also a vector, will be the force, which is a vector, divided by the mass, which isn't a vector. So I've underlined force and acceleration because they are both vectors. So it's 65,000 root 3 I plus 5,000 J, all divided by the mass of the tanker, which was 20 million kilograms. I'm going to do a little bit of simplifying. There's three terms here, two in the numerator, one in the denominator. They all have a common factor of 1,000, or could go even further. They've all got a common factor of 5,000. It's up to you whether you bother simplifying it or not. We could do that or just go straight for finding the magnitude and direction. I am going to slightly simplify this. I'm going to divide all three terms. That's both terms in the numerator and the one in the denominator. I'm going to divide them all by 5,000. So there we go. I divide them all by 5,000. I could also write this as 1 over 4,000 times 13i plus j. Lots of different ways I could write it. Now, two things we need: the magnitude and then the direction of this vector. So the magnitude of A, we can use this notation. The vertical line surrounding A means the magnitude of A. That comes from Pythagoras. So that's going to be the square root of the I component squared plus the j component squared. And then, well, all square rooted. I think I said square root, I can't remember. So the I component is 13 over 4,000. We're going to need to square that. The j component is 1 over 4,000. We're going to need to square that as well. Add them together and then square root the whole thing. This will give us the magnitude of the acceleration. I've just noticed I lost a root 3 earlier. I had lost, it was here and I've lost it there. So I'm going to fix that now. I lost that root 3. So there's 13 root 3i. Sorry about that. Let's fix that now. 13 root 3 times I. And then again in there it'll be 13 root 3. And we'll have a root 3 in here as well. Sorry about that. So please update your notes if you didn't notice that I made a mistake. Now for this acceleration, I get don't get 5.63 times 10 to the power minus 3. It's an acceleration, so the units will be meters per second. That's in standard form because it's such a small number. You don't have to write it or get it out of standard form, but it's worth practicing that. So that'll be 0.00563 meters per second every second. I've rounded that to 3 significant figures. So presenting your answer in either of these two formats would be correct. Make sure you've got units though, and show that you've rounded. That's a very, very small number. Is that to be expected? Well, think about the context here. We've got a 20,000 ton oil tank, well, some kind of tanker. I don't know if it's oil or not. They're not generally going to be too nimble, so they're not going to accelerate that quickly because they're so enormous. So such a small number does make sense here. Let's go now and find the direction of this acceleration. Now if we go back to the acceleration itself, I don't really need the 1 over 4,000 when I'm just thinking about the direction. If I draw a quick diagram, the acceleration is in the direction 13 root 3 I plus j. It's parallel to that direction. I can safely ignore the 1 over 4,000 because that just makes the vector shorter. It doesn't change the direction. So for this bit, I can ignore the 1 over 4,000. I'm going to find theta, and that'll give us the direction. So remember, I and j are in the horizontal and vertical directions. So this is 13 root 3 in the I direction and 1 in the j direction. So tan theta, which is opposite over adjacent, will be 1 over 13 root 3. So we can do inverse tan or arctan, means the same thing, of that fraction, and that will give us our angle. And that is 2.54 degrees to 3 significant figures. You can give your answer in radians alternatively if you want to. And when you're describing a direction in a question like this, it's a good idea to say above the x-axis or above the dotted line in the diagram. The fact I've got a diagram over here as well, that helps because it supports your answer. So your answer for your direction is not just a number, but it's a number with a description as well. Okay, that concludes this example.